All right, this is our last chapter on the elements. And this is the chapter where we kind of put it all together. We look at the periodic table as a whole, and we look at the construction of it and the organization of it, so we can understand all of the properties of the different elements that are on it. Because after this, once we get to chapter 7, we're done talking about individual elements, and then we get into talking about putting elements together to make compounds. Right, so this is our last chance to really learn all that we can about that periodic table of elements. So for chapter 6, right, so this is the chapter that we're working with here. The chapter 6 on the periodic table is split up into, again, objectives. So make sure that you are aware of what you need to be learning by the time we get done with this chapter. So organizing the elements, where again we're going to look at what the organization and the history of the periodic table is. We're going to look at the different families on the periodic table and classifying the elements. And then finally we're going to look at periodic trends that you can get as you look across and down on the periodic table. All right. Well, the big thing that I want you to get out of this lecture here is I want you to understand where this periodic table of elements originally came from. Okay, the periodic table of elements didn't just appear. Somebody didn't just come up with one day and then we've been sticking with it all of this time. It's a gradual thing that has occurred over many, many years. If we go back into the times before chemistry was even a science, and alchemists were at work. Alchemists would have been people who were trying to turn the ordinary into the extraordinary. Like, for instance, there were a number of people in the world that thought that it was possible that if you took like a plain old rock off the street and you mixed it with just the right other things, that poof, eventually you could turn that rock into gold and you could get rich. Right? And there were enough people that thought that there's got to be a way to do that, that they spent a lot of time and actually a lot of money. You can see in this picture here, right, this is from 1682, and this is somebody's sort of laboratory that they have made in their house, right? And they have developed all of these different vessels and all of this different equipment that they're using, and probably have been gathering substances from all over the world and trying to find a way that they can mix these different substances just the right way and poof, turn something into gold. And you can see that they started coming up where they were tired of writing what the substances were, so they would make up little symbols for all the different substances. And different substances back then weren't necessarily all the elements that we know today. For instance, they had familiar ones like gold and silver and iron and mercury. But there were also substances called Jupiter and Venus, right? There was aqua fortis and aqua regis and spirit of wine, and they even have water and fire as part of the elements. Now today, we have a much better understanding of what an element really is. And of course, after this point in history, once we start getting into the 1700s, chemistry, the actual science, starts to take hold. Because at this point where the alchemists were working, they weren't really trying to study the substances and figure out how they worked. They were just trying to get rich quick. So if we kind of fast forward just a little bit and we get to talking about John Dalton. You remember John Dalton. He came up with the atomic theory. That's the listing of how atoms work. He was one of the early famous chemists. And one of the things that he did is he started to write down all of the elements, the simplest substances that we could find that couldn't be broken down any further. He started to write them down in a table. Now, this is not a periodic table of elements. This is just a table, a list, basically, of the elements that they knew of in 1808. And you can see that some of them, they were simply using symbols still to represent, and some of them, they actually had letters for them. Now, if we move a little bit further into the mid-1800s, this is when this idea of a periodic table of elements starts to develop. So a periodic table of elements is going to be a table that isn't just a list, but actually goes in order of the properties of the elements. So John Newlands was one of the first people to ever try this. They took all of the elements that they knew of in that time, so in 1865, and he listed them in order of their properties. Like, for instance, you might have the lightest to the heaviest, or the most reactive to the least reactive, right? And he tried to put them in order based on those properties, and they would periodically change. That means over and over they would change just slightly as you went through the different rows and the different columns that were here. In fact, he thought he was onto something. Right? If you start to look at the lightest elements like hydrogen and lithium and beryllium and boron and so forth, if you go in order, their properties seem to change nice and evenly, almost like notes in music, right? And we know there's 8 notes in music, and he thought that every 8 elements, it started over again, and then it went and changed again, kind of like the octaves in music. And so he called this the law of octaves. And it worked really, really, really well until you start to get to the really heavy metals and other elements, and suddenly it falls apart. And so John Newlands was on to an idea. It just was the wrong idea. He didn't have them set up in the right way. And so there was other scientists and other chemists that started to take this idea and say, you know what? I bet you there is a way that does work, however. But it wasn't until there was a chemist, a Russian chemist by the name of Dmitry Mendeleev in 1869. And Mendeleev actually came up with what we would call today the first working periodic table of elements. And the reason why it worked is, one, he came up with a way of putting them in order, not just by their properties, but also by figuring out how heavy each one of them was compared to each other. Like, for instance, it was really easy to tell that hydrogen was the lightest. And if you compare hydrogen to lithium, lithium is 7 times heavier, so he just called lithium 7. And beryllium is 9.4 times heavier than hydrogen, so he called it 9.4, and so on and so forth. And he gave all of the elements, again known at that time, he gave them all numbers. At the time, we called them atomic weights. And so all of these elements were put not in just order of properties, but also their weights. And so he grouped them together based on their properties. He also put them in rows that he called periods. So we have groups, which are the columns. We have periods, which are the actual rows here. And all of these elements seem to all line up nicely, except that he was getting these holes. He was getting these empty spots. Like calcium fits in well in group 2, along with beryllium and magnesium. And titanium fits in well with silicon and carbon, according to Mendeleev. But in group 3, there seemed to be an element that should have been right here between calcium and titanium, probably somewhere around a 44 atomic weight, that would fit, and it would have similar properties to boron and aluminum. Right? And he was sure that he was onto something here, and he said, you know what? I think that in a few years, when we start to discover new elements, we will eventually discover an element that has an atomic weight of about 44, and it will have similar properties to boron and aluminum. And what happened? In a few years, we did discover a new element that fit just perfectly right there. and one that would fit here, and one that would fit here, and one that would fit here. And so people started to realize that Mendeleev was onto something. He actually came up with an order of the elements that makes sense and can predict new elements. And that's really important. And that's why he is known as the father of the periodic table. So Dmitri Mendeleev, the father of the periodic table, started this idea. But you can tell right now that this looks nothing like the periodic table that we use today in the year 2020, right? Where this looks nothing like the one that we currently use. And so there's going to be some changes that happen over the next 150 years. Okay? And again, this is the reason why Mendeleev and his periodic table was so important, is because he was able to predict the properties of elements that had not yet been discovered. Right? So his version of the periodic table was the most useful. So fast forward about 50 years, and about 50 years from then, we start to discover that the atoms have other parts to them, like protons and neutrons and electrons. And we kind of talked all about that in chapter 4. So by 1914, a guy by the name of Henry Moseley says, you know what? I think we can redo this periodic table because the idea of the proton becomes really important. Elements should be defined by how many protons they have. And so if we take and we list the number of protons, their atomic number, next to them, instead of their atomic weights, and then we put them back in order, kind of like Mendeleev did, right? We put them back in order. We still put them in groups. We still put them in periods. Things actually work out better. And of course, you can see by 1930, we know a lot more elements than we did in 1865. There are a lot more elements that were discovered. And this starts to become a little bit like the one we see today. If you look through the groups that are listed here, right? It starts with group 0, so that'll be the first group. And then each of these next few groups has an A and a B group to it. So if you count up all the total number of groups, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, if you look on your current periodic table, right, the current periodic table of today has 18 on it. So we're getting pretty close. And then if we count up how many periods there are, there's 1 here, 2, 3, 4, 5, 6, 7 periods. The one we use today has 7 periods on it. And so this is starting to come into view. Again, it still doesn't look exactly like the one we have today. This is a nice rectangle. And the one we have today doesn't look all nice and rectangular like this. So there's one big other change that had happened, and it happens right around World War II. Okay? Turns out that in World War II, we were on the hunt for other elements that could be used in things like atomic bombs. Right? And so we had scientists that were working in this country at looking at what other elements could be created. Not just discovered, but could you create new elements that could help us do other things? And so Glenn Seaborg at UCLA actually researches and discovers that you can create new elements past uranium. And uranium was always thought to be the heaviest element that there is. It is certainly the heaviest natural element that occurs in nature. But he learned that you can create new elements by actually adding more and more protons to the nucleus. In fact, he even wins a Nobel Prize for this, and we name an element after him eventually. Element number 106 is called Seaborgium in his honor. So by the time we get to that point and we've discovered all these new, much heavier elements, the periodic table starts to get really long and really big. And it comes, you know, in this weird shape, and it doesn't fit on a piece of paper very well if you wanted to print it out. And so the very last change is, let's take this part right here, right, and let's pull it down to the bottom. These are all the elements that come after uranium here. And so we pull it down to the bottom, and those are the trans-uranium elements. And so when we're done, we still have groups. Those are the columns that go up and down. We still have periods. Those are the rows that go across. But this is the shape that our periodic table today takes. Now, it doesn't have to stop there, right? It's possible that the periodic table in the future could look something like this, right? I know it looks really, really weird, but to tell you the truth, all of the same elements that we have on our periodic table right now and this one are exactly the same. In fact, they have the same groups and the same periods that ours does now. It's just wrapped into a different shape. Now, I'd say this one's really hard to read, and it's probably why it never took off as a viable candidate, as a periodic table that we would all use. But it could be. I mean, it could even look like something like this, right? This is a three-dimensional periodic table. We still have 7 periods. We still have, if you go all the way around this thing, we still have 18 groups. They're all still there, although it's still really hard to read. I don't think that's the way we were going to go. This is something actually, by the way, you can purchase. It's called an elementary. You get it. Okay. So this idea of the periodic table over history is something that I kind of want you to understand where it came from. Why does it look the way that it does today? Who was responsible for creating the first ones? All right. And then we're going to talk more about the actual information and properties on the periodic table the next time.